This is a really quick comparison of finite difference method and finite element method. It just covers a few of the basics to give you an idea of when you might choose one or the other. So first, we have been solving problems using the finite difference method. This involves discrete equations where you take the governing equation, the governing differential equation, and you discretize that equation to make differences between neighboring nodes. U of x plus delta x, u of x minus delta x. And we discretize these derivatives, and when we do that, we're generally assuming an orthogonal structure that nodes in our finite difference mesh are placed along the x and y coordinates. Once we discretize the equations, we can apply the equation at each node, and given an initial guess at the solution, we can calculate a residual at each node by just applying this difference equation. Put all those together into a system of equations, a matrix. We can solve that using various iterative or direct solution techniques and get the final solution to our boundary value problem. Fairly straightforward. We've done that in 1 and 2 dimensions in this course. And the powerful thing about finite differences really is that you can often write your own software. You don't need prepackaged software. Although there's a class of computational solvers called finite volume method. And this finite volume method will take grids that have structured grids that have been warped into strange shapes, and it'll apply the finite differences equations using the correct geometry and physics on those warped but structured grids. Very similar to finite differences, fast solution and used in many fields. The finite element method, which we saw earlier in the video by Dr. Schuster, it approximates a solution to the boundary value problem using piecewise continuous elements. So the solution within each element satisfies the governing equation, and each element is stitched together to all of its neighbors so that the solution is continuous across each of them. And this works just fine in both structured and structured grids because the solution is already is built into the individual elements and the shape functions used in there. Now, what do I mean by shape functions? Or they're also called basis functions. This is a function that interpolates the quantity of interest. So it might be temperature, it might be stress, it might be voltage. It interpolates the solution across each one of the elements so that it's continuous across the element. Here's an example of a linear basis function in one dimension. And if you look at this in an element here centered at node 0.2, the basis function will have a value of 1 at the node and 0 everywhere else. So in this graph, we might see two side-by-side elements, one between 0 and 0.2 and the other from 0.2 to 4. So you have a continuous solution where the value at the node is 1. So you can use that basis function to build up a solution where the value at each node is calculated, and then it's interpolated across the elements using a set of these basis functions. For instance, here's a set of, what is this? A bunch of basis functions where each one of the nodes has some combination of basis functions where the value is 1 at the node and 0 elsewhere. And so you can see if you just solve for the nodal values, these functions will interpolate the solution everywhere else in our volume and our geometry. Once you have these basis functions, once you've created the appropriate functions within each element, you stitch these things together by matching the boundary conditions and then minimizing the global error in your solution by building this system of equations. You build your system of equations, which includes the stiffness matrix K, the forcing function on the right F, and the nodal values or degrees of freedom are U in this case. We've been looking at temperature, so I'm using U here. You can solve this system of equations using iterative or direct solvers. It doesn't matter. But either way, you get a solution that is in all ways similar and equivalent to the finite difference solution. These two methods are both powerful and both used commonly by researchers and people in industry. So when to use one or the other? Well, finite element methods, because they can use unstructured grids more easily than finite difference methods, you often use finite elements in complex geometries. There's a lot of commercial software out there available, and often when you have inhomogeneous properties which change throughout the volume, it's a little easier sometimes to incorporate that into a finite element grid as opposed to a finite difference grid. Finite difference grids, however, are usually used when it's a fairly simple geometry or a geometry that can be decomposed into these orthogonal meshes. There is custom software for it, but it's not nearly as common. But the finite difference method is fast and very memory efficient. So larger problems, if you can use finite differences, sometimes they become more computationally solvable because it's a more efficient method numerically. You might see finite elements used in mechanical modeling. Here's an example of a tire being deformed by the pressure on it. Whereas larger problems, and some of the largest problems we handle at this point are weather models where you discretize points along the Earth and in the atmosphere down to, you want to get down to, less than a kilometer in space. A kilometer is a large distance across the Earth. But these models are limited by the computational abilities. And so you might use finite differences because you can use a more dense mesh and solve these things quicker than using finite elements. Both very powerful methods. It's you as the modeler, it's your choice to find one which is most effective for your application.